The work done by a force is given by the following equation. Work, W, is equal to the force that's doing the work multiplied by the displacement over which the force acts, multiplied by the cosine of the angle between the direction of the force and the displacement. The unit of work is the Newton meter, which is redefined as the joule. Okay, so the unit is the joule. If the force is a net force, then we have net work. And net work can be shown to be equal to the change in the kinetic energy. So when net work is done on something, it transfers energy from one system to another, and that energy is in the form of kinetic energy. Now, kinetic energy is defined to be 1/2 mv squared, and since we have a change, it would be 1/2 mvf squared minus 1/2 mvo squared. Okay, so there's our equation for net work, and this is known as the work kinetic energy theorem. Let's take a look at the work now done by a conservative force, such as the force of gravity. The work done by the force of gravity, I'll call it Wg, can be shown to be equal to the negative of the change in the gravitational potential energy. Delta PEG stands for the change in gravitational potential energy, where potential energy is equal to mgh. So we have a change in potential energy, but it's the negative of that. So what we end up with is mgho minus mghf is the work done by gravity. Now, suppose the work done by gravity is the net work. So if that's the case, we can set the work done by gravity equal to the net work, or in other words, the negative change in the gravitational potential energy is equal to the change in the kinetic energy. So negative change in gravitational potential energy is mgho minus mghf. The change in kinetic energy is 1/2 mvf squared minus 1/2 mvo squared. Putting the originals on the left and the finals on the right, we get an expression which is referred to as the conservation of mechanical energy. And it's very useful when solving roller coaster problems or even projectile motion problems in some cases. Okay, so this is known as the law of conservation of mechanical energy. Let's take a look at what happens when there is non-conservative forces like friction. So for example, let's say you drop a ball. If there were no air, the work would be done simply by the force of gravity, which is a constant. So we would have that the work done by the force of gravity is equal to the change in kinetic energy of the ball. But if there's air, there's a drag force upward on the ball at all times. And this force changes, right? It increases as the speed of the ball increases. So we would have to add here the work done by drag to the work done by gravity and set that equal to delta KE. Now the work done by gravity, recall, is equal to the negative of the change in potential energy. So suppose we want to figure out the final speed of the ball after it falls through a distance which I'm just going to call h. And let's say it starts from rest. So that's what we get. Okay, this would be the original potential energy. Okay, h is the height of the ball initially. This is the work done by the drag force. You add these two together, and that's going to be equal to the kinetic energy of the ball just before it hits. So the work done by the drag force, since the drag force is directed opposite the vertical displacement, which is directed down, this is going to be a negative value. So whatever this turns out to be, it will be a negative value. Now, we could actually figure that out if we knew the final speed of the ball. WD would be equal to 1/2 mvf squared minus mgh. Right? So in this case, the potential energy that the ball has before being released is greater than the kinetic energy the ball has down here, which means that some of the original potential energy was converted into heat due to the drag force doing work on the ball.